Our last section for this chapter is 2.8, and that is about density. So our aim for this section is to define density and its units. So we want to look at what it means to be dense, what density is referring to in terms of a unit that we can measure, and how we measure those different units using different unit labels that we've already talked about. So density is mass over volume. We can think of it as how heavy something is for the space that it takes up. So two objects that are the same size, if one is heavier than the other, it is said to be more dense. So we can abbreviate this by saying density is big D, mass is little m, and volume is little m. So D equals m over V is how we would define density in variables. We can define it in words as the amount of matter in a given three-dimensional space. We know mass measures the amount of matter in an object, and volume represents three-dimensional space. So if we're looking at a picture, how to visually represent density, the picture on the left is looking at an object with high density. It has a lot of matter in a comparable three-dimensional space. We can see on the right, we have the same amount of three-dimensional space. However, we have fewer particles there. So this sample is less dense or low density compared to the high density sample. These are relative terms. So if we're just looking at one of these, there's no way for us to know if the density is high or low. We have to be able to compare it to something else. So if we're looking at the high density picture, we are able to say that's high density because we're comparing it to the lower density picture on the right. I could have another picture over here and have it packed even more tightly, even more matter in the same three-dimensional space. And then I would be able to say that the picture to the far left has an even higher density than the one that would be in the middle. So density is a relative term. I need to use high or low to compare them to each other. If we're calculating density, again, we can say density equals mass over volume. Mass, we know, is units of grams. Volume, we can use units of cubic centimeters, or we can use units of grams per milliliter. Remember, cubic centimeter and milliliter represent the same quantity. We had talked about when we would use cubic centimeters versus milliliters. Remember, cubic centimeters mean we're looking at a regularly shaped solid. And if we're looking at milliliters, that means we're looking at a liquid. We measure liquids in milliliters. We measure the sides of a regularly shaped solid in cubic centimeters. Now we can rearrange this equation. You really have to be very comfortable solving for the different variables in the density equation. So in this case, if we're solving for m, we're looking at equation number 1, and we're looking at how we might be able to isolate m to get m by itself. Notice in this equation that mass is divided by volume. So what we'd want to do to get mass by itself is to be able to multiply both sides by volume. And if we do that, volume cancels out on the right, and we get that m equals d times b. So this is a way, just knowing the basic density equation, that we're able to rearrange it to solve for another variable. So if we're looking at how units cancel in this situation, we have density, which is in units of grams per milliliter, and we are multiplying that by volume. And if we do this, we can see milliliters is on top and divided by milliliters on the bottom. A unit divided by itself cancels out, becomes 1. So what are we left with? Units of mass, or grams. So you can approach this in either way. You can look at rearranging the equation in terms of its variables, or you can look at how the units cancel to be able to solve for your desired unit. For the third equation, the only thing left to solve for is volume. So we can look at equation 2, and we can look at what we would have to do to get volume by itself. In equation 2, we had to multiply volume by density to give us mass. So in this case, what we're going to have to do is undo what was done to it, which means we have to divide both sides by density. So here we get that volume equals mass divided by density, because the density values canceled out in equation number 2. Looking at this in terms of the units actually canceling, we see that mass in units of G divided by grams per milliliter. Now this gets a little tricky. Nobody likes fractions, especially when there's a fraction in the denominator. So what we can do, instead of dividing by a fraction, we can multiply by its reciprocal. So when we do that, we can see that grams times milliliters over grams will give us our answer. And our answer here is milliliters because the grams end up canceling out. So use one of these three equations to be able to solve for whichever variable you're being asked to solve for. If you're asked to solve density, you're going to use equation 1. If you're asked to solve for mass, you're going to use equation 2. If you're asked to solve for volume, you're going to use equation 3. You can memorize the equations if you want to, but I don't want you to focus on memorizing. I want you to focus on actually learning how to manipulate an equation to solve for an unknown variable. That limits what you actually have to keep in your head and teaches you how to reassemble or rework an equation to solve for the variable that you're looking for. We're going to be solving for x a lot in this course, so the sooner you learn how to actually rearrange these equations, the quicker it's going to pay off. Sample problem. It says mercury has a density of 13.6 grams per milliliter. What volume of mercury is needed to obtain 225 grams of metal? So we want to first start by listing what we know is going on in this problem. We have two pieces of information. We have a density that's equal to 13.6 grams per milliliter and a mass equal to 225 grams. The volume is what we're being asked to solve for. What volume of mercury? So we know the only thing that's missing from the density equation is volume. So we want to think about what we're actually solving for in this equation and how to rearrange that density equation that we're very familiar with because we know that density equals mass over volume, how we can rearrange this equation to be able to solve for V. We can go back to those three equations that we looked at just a minute ago, and we can see how to solve for V. But there are two different ways to approach this problem. So if you can't remember how to rearrange the equation, or you can't remember those three different equations and to choose the one that you need, there's another fix for that. The first one is using the density equation. So if we look at the density equation and we remember how to solve for volume, we should remember that volume equals mass over density. So when we do that, and we just plug in our values because we know that the mass is 225 grams, we know that the density is 13.6 grams per milliliter. We already saw how the units canceled in a problem like this, so we don't need to show those units canceling. We know just based on the equation that the units will end up canceling. So we can just put this in the calculator. And we get 16.5441 as our final answer. We'll discuss sig figs and how to apply them here in just a minute. But the second approach to this problem is using dimensional analysis. This is my chosen method because, like I said, I don't have to remember how to use an equation, how to rearrange an equation, and it's much easier to see how units end up canceling in a problem like this. So with dimensional analysis, we always start with our given piece of information. The problem here is we have two given pieces of information, but one of these is never to be started with. This is a conversion factor. We never start a dimensional analysis problem with a conversion factor. We always start with just our single piece of information because the conversion factor is what we use to change that unit on the single piece of information. So we start with 225 grams. If we do that, we draw our line. We put the unit we started with on the bottom of that line. So grams goes on the bottom. We want to make sure that unit cancels out. What we're going to put on top is then milliliters, because we're told right here that our density is 13.6 grams per milliliter. 13.6 goes with the grams on the bottom, 1 goes with the milliliter on the top. At this point, since I was asked to solve for volume, I am in units of milliliters, so I can stop and I can answer my question. And you'll notice these answers are the same. 16.5441 in both cases. I'm doing exactly the same math. 225 divided by 13.6, and in this problem, again, 225 divided by 13.6. Now, we need to remember to take into account significant figures. Which number is guiding the number of sig figs in my answer? They both have 3, but we never use a conversion factor to guide the number of sig figs in our answer, because remember, conversion factors are exact. They have an infinite number of sig figs. So what is guiding my answer is this single piece of information, and that single piece of information has 3 sig figs. So remember, we're coming over to our final answer. We're cutting it off at 3 sig figs. We're looking at the number we cut off, which is 4, and then we are rounding according to that number. Remember, 4 keeps the number before the cutoff the same, or rather rounds it down to its base level. So we end up with 16.5, and remember, numbers mean nothing without their units, so our final answer is 16.5 milliliters. Stop your video, take a minute to do these practice problems, and then we will come back together and discuss the answers. In the first problem, we're told the density of aluminum is 3.69 grams per milliliter. The volume found by displacement is 1.50 milliliters. What is the mass? First of all, you might be asking, what is displacement? Displacement is if you have a container of liquid and it's at a certain volume. In this case, say maybe 5.0 milliliters. Then we're going to put a sample of aluminum in here, and then we'll just say that's maybe a cube. And when we put that sample of aluminum in here, the volume then increases by the amount that that cube is displacing the liquid. And say the new volume comes up to 6.5 milliliters. In this case, we would say, and as stated in the problem, the volume found by displacement is 1.50 milliliters. That tells us that that volume took up 1.5 milliliters of three-dimensional space. So we want to know what the mass is. So we can look back at our original equations. We can approach this from one of two perspectives. We can look at rearranging the equation, or we can look at dimensional analysis. I'm going to show you dimensional analysis first. 1.50 milliliters. We're going to use the density then to convert to mass. 1 milliliter on the bottom, 3.69 grams on top. So we can see here that milliliters end up canceling, and then we end up with units of mass or grams on the top. So then when we put this in the calculator, we're going to enter 1.50 times 3.69, and we end up with 5.535 grams. Sig figs in our answer goes back to the original number. We had 3 sig figs, so we want 3 sig figs in our answer. We're going to cut it off right here, which means we end up with a final mass of 5.54 grams. You could also do this in terms of the equation that you're going to use to calculate this, and we can write the equations really quickly up here. We know that density equals mass over volume. We know that mass equals density times volume, and we know that volume equals mass divided by density. So we can write those down at the beginning just to remind ourselves which equations we're using, or we can use dimensional analysis. You can see it works out the same way. If I'm looking back at the dimensional analysis problem I just solved, 1.50 milliliters is volume, and we multiplied the volume by the density, and volume times density, as we can see according to equation 2 up here, equals mass. For number 2, the dimensions of a rectangular solid are 1.30 centimeters, 15 centimeters, and 2.5 centimeters. What is the volume? Now, we don't have a liquid volume here, so obviously we're not going to be measuring in milliliters. The other option for measuring in volume is cubic centimeters. And cubic centimeters means, again, if we're visualizing a cube, we know that the volume of a cube is length times width times height. So we have three-dimensional space. Remember, that's what volume measures. So we've got three dimensions. We've got 1.30 centimeters times 15 centimeters times 2.5 centimeters. So if we're calculating volume, the answer is going to be given to us in cubic centimeters, or centimeters to the power 3, and we're multiplying 1.30 times 15 times 2.5. And we get for our answer 48.75 cubic centimeters. And we can see we have actually two values that have only two sig figs. So we're going to end up with two sig figs for our answer. And that is actually an 8. Now, to round this number to two sig figs, we're going to start from the left, cut it off after two sig figs. So the answer here actually ends up being 49 cubic centimeters. For the last problem, it says, what is the density if the mass was found to be 6.0 grams? And this is an extension of part A. Notice it says part B in front. So we're asked to calculate density. Density equals mass over volume. We've been given a mass. We know our mass is 6.0 grams. We also have a volume. Now the problem here is we've been given two different volumes from above. We have the rounded version and the unrounded version. When you're applying sig figs, if I am being asked what is the volume, I want to apply sig figs to this answer. But if the question has a second part, I want to use the unrounded answer. I don't want to apply sig figs until the problem is completely over. So I'm going to use 48.75 cubic centimeters as my volume for part 2. So when I put this in the calculator, 6.0 divided by 48.75, and this gives me 0.1230769 grams per milliliter, grams per cubic centimeter. Remember, both of those units are equal. Now I want to make sure that I'm observing sig figs. I need to round this answer to two sig figs based on the number 6.0. So therefore, I'm going to cut it off right here. The 3 rounds the 2 down, or rather keeps it the same. So this ends up being 0.12 grams per, and in this case, I wrote milliliters above, but cubic centimeter would be more appropriate to remind us that we are measuring a solid, regularly shaped object rather than measuring volume of a liquid.